Hello everyone. Today we will discuss about the problems on deflection of PSC members. First problem: a PSC beam of rectangular section 120 mm wide, 300 mm deep is pre-stressed by a linearly varying cable as shown in figure. The beam supports a uniformly distributed live load of 4 kN per meter. The effective force in the cable is 200 kN. Estimate the short-term deflection of the beam under pre-stress plus self-weight plus live load. Assume E 38 kN per mm square, unit weight of concrete 24 kN per meter cube. So this is the cross section given, and tendon profile it is given shown in the figure, so no need to worry. So this beam will be given. So here you can observe the cable has straight portions with eccentricity of 50 mm at midspan and eccentricity of 0 at supports. And let us take given data. E elastic modulus of the cross section it is given 38 kN per mm square. If you convert Newton per mm square, it is 38 into 10 power 3. Then moment of inertia 27 into 10 power 7 mm power 4, that is BDQ by 12. Then load prestressing force applied is 200 kN. Dead load cross section into density of concrete is given as 24. So cross section into density we will get 0.86 Newton per mm. Then live load it is directly given 4 kN per meter is nothing but 4 Newton per mm. Then span of the beam is 6 meter. So now, as we discussed earlier, the beam will be under deflection with respect to 3 parameters. One is deflection due to dead load, deflection due to live load, and deflection due to pre-stressing force. So first let us calculate deflection due to dead load and live load. So we know dead load will be in the form of UDL. So UDL, if you draw the bending moment diagram, it is shown here. It will be in the shape of parabola with maximum bending moment at midspan of WL square by 8. Here you need to remember this 5 WL power 4 by 384 EI, this formula, or how to derive that formula you need to remember. So both I have given. How the formula is arrived, it is given and at the side. Half of the span we are going to consider, half span of the bending moment diagram, and area moment of area of the half span bending moment diagram, that is the bending moment diagram over the L by 2 span with respect to support. So if we consider directly formula 5 WD L power 4 by 384 EI, on substituting we will get 1.42 mm is the deflection with respect to dead load, and it is downward deflection. Same way, let us go for live load. In question it is given live load is also uniformly distributed load. So the formula will be same, 5 WL power 4 by 384 EI. On substituting we will get 6.58 mm, and again it will be downward deflection. Now we have calculated deflection due to dead load, due to live load, and the third thing remaining is deflection due to pre-stressing force. So as I explained in theory part, deflection due to pre-stressing force is also calculated on the basis of bending moment diagram. The bending moment diagram will be, the shape of the bending moment diagram will be same as that of the profile of the cable or tendon, with maximum height of product of prestressing force and eccentricity. So since we have triangular shape profile, bending moment diagram with respect to prestressing force will also be in triangular shape only with a maximum height of P into E. By using this deflection formula, bending moment diagram, we need to find out the deflection due to prestressing force. So if you consider a span of L, as we know, we are going to consider half of the span, bending moment diagram in the half of the span. Here deflection due to prestressing force, since it is a triangular shape, moment of area of bending moment diagram over half of the span with respect to support. So half of the bending moment diagram means it is represented as shaded area. So area of shaded area is half into base L by 2 into height P into E into the bending moment with respect to support, means it is you are measuring the centroidal distance of triangle from apex, that is 2/3 of L by 2 or 2/3 of base 2/3 of L by 2 divided by EI. Now for that, on simplification we will get PEL square by 12 EI. Then substitute the values. P is 200, E is 50 mm, L is 6 meter, that is 6000 mm upon 12 into E 38 into 10 power 3 and I is 27 into 10 power 7. On simplifying we will get 2.92 mm, and we know deflection due to prestressing force is upward deflection. We need to remember deflection due to dead load and live load will be downward deflections, and those will be considered as positive, and deflection due to prestressing force is upward deflection and it is considered as negative. So we need to find out short term deflection. It is YD plus YL minus YP. We have calculated the values, substitute and we can calculate the final deflection. It is of 5.07 mm. Next problem. A concrete beam is prestressed by a linearly varying cable having eccentricities as shown in the figure. The force in the cable is 350 kilonewton. The beam supports a concentrated load of 20 kilonewton at center of the span. If E is equal to 38 kilonewton per mm square and loss ratio 0.8 and creep coefficient 1.6, calculate or compute short-term deflection under pre-stress and self-weight, long-term deflection under pre-stress, self-weight and live load. Observe the question carefully. Here it is given short-term deflection under pre-stress and self-weight only, and long-term deflection we need to consider live load. So cable profile given is same as in case of first problem. It is triangular profile, but it has eccentricity of 50 mm at midspan and 25 mm at supports. It has eccentricity at both. support as well as mid span, and cross section is given. The span of the beam is 8 meters. So let us take down the given data. E, modulus of elasticity of steel, moment of inertia BD cube by 12, P 350 kilonewton is given, dead load cross section into density, we will get 1.08 kilonewton per meter, length 8 meter, W 20 kilonewton. Remember, it is concentrated load. Now first let us calculate deflection due to dead load. So dead load is uniformly distributed load, UDL. For UDL we are having a formula, YD equals 5WL power 4 by 384 EI. On substituting the values we will get deflection due to dead load as 4.49 mm. Then deflection due to live load, here if you draw the bending moment diagram for live load, that is point load, it will be in the form of triangle with maximum bending moment at midspan of WL by 4. If you take deflection by using moment of area of the bending moment diagram over half of the span and simplifying, we will get WL cube by 48 EI. It is also shown in the theory part, you can refer, and substituting the values we will get 16.63 mm. Then deflection due to prestressing force, here it is triangular shape with eccentricity at both midspan as well as support section. So first the bending moment diagram will be considered as it is as of the same tendon profile, that is triangular shape with total eccentricity, the summation of support eccentricity and midspan eccentricity, total eccentricity or depth of the cable we need to consider. So that is P into E1 plus E2, and for prestressing force above the neutral axis, that is for support eccentricity, we are going to consider rectangle bending moment diagram with magnitude of prestressing force into only support eccentricity. These two diagrams we are going to consider. Here E1 is the eccentricity at midspan and E2 is the eccentricity at support. Then here the deflection of prestressing force below the neutral axis will be negative and above the neutral axis will be positive. So here the rectangular portion what we have considered, it will be treated as positive deflection, and negative triangular bending moment diagram what we have considered is negative deflection. So total deflection due to prestressing force will be calculated as area of hatching force in the rectangle diagram, P into E2 into L by 2 is the length into breadth, area of rectangle, into L by 4, that is length by 2 will be the centroid for rectangle. So L by 2 is the length of the rectangle and divide by 2 it is L by 4, it is positive, minus, now we are going to consider triangle, half into base is L by 2 into height is P into E1 plus E2, that is both eccentricities we have considered, into 2/3 of base, 2/3 of L by 2 divided by EI. On simplifying we will get PL square by 24 EI into E2 minus 2E1. On substituting the values we will get deflection of minus 5.45 mm. Short term deflection, see this minus indicates prestressing force is coming in downward direction only, so you should not neglect this minus, you have to consider. Wait, No, it is representing upward deflection. Prestressing force is giving upward deflection, so you have to consider minus. Short term deflection, yp plus yd, yp value is minus 5.45 and the deflection due to dead load is 4.49. On simplifying we will get minus 0.96 mm upward deflection. Now long term deflection, we have 1 plus phi into yd plus yl minus neta np. Neta is loss ratio and phi is the creep coefficient. 1 plus 1.6 into 4.49 is the dead load deflection. 16.63 is the live load deflection minus 0.8 into 5.45. That is deflection due to prestressing force. On simplifying we will get 57 mm as the overall long term deflection. Next problem, a pre-stressed concrete beam of rectangular section 120 mm wide and 300 mm deep spans over 6 meter. The beam is pre-stressed by straight cable carrying an effective force of 180 kN at an eccentricity of 50 mm. It supports a superimposed load of 4 kN per meter. Compute the deflection at the following stages and check whether they comply with IS code specifications. First one, pre-stress plus self-weight. Next one, pre-stress plus self-weight plus superimposed load, including the effect of creep and shrinkage. Assume creep coefficient 1.8 and EC, Young's modulus of concrete or section, both are same, 36 kN per mm square. So here we have straight tendon with uniform eccentricity of 50 mm and cross section is 300 by 120 mm. We know for straight tendon, bending moment diagram due to prestressing force will be rectangle itself with a magnitude of prestressing force into eccentricity. So P is 180 kN, E is 36 kN per mm square, I 270 into 10 power 6 mm power 4, WD cross section into density of concrete, WL it is directly given, length of the beam is 6 meter, phi 1.8 and eccentricity 50. Deflection due to dead load, obviously dead load will be UDL, 5 WDL square power 4 by 384 EI. Substitute the values, we will get 1.5 downward deflection. Then deflection due to live load, again live load is also UDL in this problem. So 5 WL power 4 by 384 EI. Substitute the values and simplify, we will get the deflection due to live load. Then deflection due to pre-stressing force. So for rectangle we will be having deflection of PEL square by 8 EI. It is derived in the derivations itself. So if you want, you can take rectangle will be the shape of the bending moment diagram with respect to prestressing force. In rectangle we are going to consider half of the span. So length will be L by 2 and height will be PE. So PE L by 2 into L by 4, that is centroidal distance, over EI. On simplifying you will get PE L square by 8 EI. Substitute the values and we will get 4.16 mm. Short term deflection due to P and dead load, YD minus YP will get minus 2.66 mm. It is upward deflection. Long term deflection 1 plus phi into YD plus YL minus YP. So phi is 1.8. Loss ratio is not given, so no need of neta. 11.98 mm and it is downward deflection. So here additional question is given. Check for what it is. Check whether they comply with IS code specifications. That is, whether the deflection occurring is within the IS code limits, that we need to check. So as per IS 1343, maximum deflection allowed is span over 250. So if you substitute span of 6000 mm over 250, you will get 24 mm. So your deflection getting is 11.98, almost 12 mm. So it is almost double than half of the allowable deflection. So the beam is safe. Next problem, a simply supported PSC beam of span 8 meter with a rectangular cross section 125 mm wide and 250 mm deep is pre-stressed by a straight cable which with a total tensile force is 210 kilonewton. The center line of the cable is parallel to the axis of the beam and 75 mm above the soffit over the middle third span and bent straight upwards over the outer third of the span to a distance of 175 mm above the soffit at the support. If EC is equal to 35 kN per mm square, calculate the deflection due to pre-stress only, then due to pre-stress and self-weight, then magnitude of concentrated load placed at 1/3 points of span, which would result in limiting the short-term deflection to span over 500. So here cable profile given is, you can observe the middle third span 1/3. If you divide the given beam into 3 parts, the center part is straight with uniform eccentricity of 25 mm and the end portions will be bent upwards to make the distance of 175 mm above the soffit of the beam at the supports. So the cross section of the beam is 250 mm, 125 mm wide by 250 mm deep. Okay, so if you take the centroid of the section, it will be 125 mm. For rectangle section, you can see the centroid will be at the height of 125 mm. So 75 mm from the soffit of the beam at midspan and 175 at the support. So eccentricity at midspan will be 125 minus 75. Below the centroidal axis it is 50 mm. Again above the centroidal axis 175 minus 125, again we will get 50 mm. So these are the given data. P is 210 kilonewton, E1 50, E2 50 we have calculated there. Moment of inertia, span, EC, dead load. So first one, deflection due to prestressing force. So as we know, the shape of bending moment diagram will be same as the shape of the tendon profile. So here it is trapezoid shape. So the same thing will reflect here, and the maximum bending moment will be prestressing force into total eccentricity P into E1 plus E2. So in shaded portion we are having two segments, one is triangular segment and another one is rectangular segment. Since the beam of span is 8 meter, if you divide into 3 parts you will get 2667 mm of each span part, and we have eccentricity even above the centroidal axis, so that we need to consider as a rectangle with magnitude of prestressing force into eccentricity above neutral axis, that is E2, P into E2. Here we have considered directly YP, deflection due to prestressing force. So if you consider first figure, you have triangle portion and rectangle portion. In hatched portion itself you have triangle and rectangle. So first let us consider triangular portion. Half into base is 2667 mm and height is 210 into 10 power 3. It is P prestressing force into E150 plus E250 into 2/3 of 2667, that is centroidal distance for the triangle. And this should be minus 2667 by 2. Here half of the rectangle we are considering into 210 into 10 power 3 into 50 plus 50 into 2667 plus 2667 by 4, that will be centroidal distance. And for this plus 210 into 10 power 3 into 50 into 4000, that is span, into 4000 by 2 divided by EI values. On excuse me, on simplifying we will get minus 10.35 mm. So that will be deflection due to prestressing force. Next, deflection due to prestress plus self weight. So first we need to calculate deflection due to self weight. It will be in the form of UDL. So 5 WD L power 4 divided by 384 EI. On simplifying we will get 7.02 mm. Deflection due to prestress plus self weight YD minus YP, we will get minus 3.33 mm. Then deflection here in third question, what you need to calculate is live load is not given, but he is given the condition that you are applying the live load at mid third points. So when you divide the given beam into 3 equal parts, the center 2 points, at those points you are going to apply the point loads, but we don't know what is the load applied. That we need to find out. For that, here condition is given, the span by 500 should be the allowable deflection. So span is 8000 divided by 500, how much you will get? 40 mm will be allowable deflection. So for that we need to find out. So if we have 2 point loads at equidistance in the beam, the centroid, the bending moment diagram will be in the trapezoid shape only. Then the same manner we are going to calculate the deflection in, and we will get the equation in terms of Q. Then span by 500 will be YD plus YL minus YP, and by substituting values and equating to span by 500 ratio we will get Q equals 6.059 kilonewton, or you can say 6.06 kilonewton. This should be the maximum load you can apply at the 2 points of 1/3 spans. Thank you.